The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. He to whom this emotion is a stranger is as good as dead. His eyes are closed. Albert Einstein said these words, and they resonate with a profound truth that echoes through the quiet halls of inquiry and the vibrant chaos of creation. To experience the mysterious is not to be lost in confusion, but to stand at the edge of understanding, peering into a vast, uncharted territory with a sense of wonder. It is the fundamental emotion, the gentle pull that has guided us since we first looked up at the stars and wondered what they were. It is the cradle from which all true art and science are born, two languages attempting to translate the same silent, ineffable text of reality. The artist and the scientist are siblings, children of this same emotion, this same rapt awe. He to whom this emotion is a stranger, who can no longer pause, no longer marvel at the sheer improbable existence of things, is as good as dead. His eyes may be open, but they do not see. They are closed to the grand, unfolding narrative of the cosmos. Beginning is the hardest step. The first words open a space, just as the first stroke of a brush on a blank canvas defines an entire world of possibilities. It is an act of courage, a commitment. Like the first glance of the girl I am about to fall in love with, a life is decided by the hint of a smile, a universe of shared moments and quiet understandings born from a single fleeting connection. I long hesitated before starting to write these words for you. This journey requires a certain state of mind, a stillness. And so, I took long walks in the woods behind my house. Here in Canada, I listened to the rustle of leaves underfoot, the slow, patient breathing of the forest, the way the light filtered through the canopy, dappling the ground in shifting patterns of gold and shadow. I was searching for the right starting point, the right path into the wilderness of these ideas. I'm still not sure where I am going, but I know the journey itself is the purpose. For some years now, my research, my thoughts, my quiet moments of contemplation have focused on white holes, the elusive, almost mythical younger siblings of black ones. This, then, is my book about white holes. But to speak of them, I must first try to describe black holes, which we now see in the heavens in their hundreds, their dark presence inferred, their existence confirmed by ripples in spacetime itself. I will do my best to paint a picture of these strange stars, what happens at their edge, this boundary we call the horizon, where the river of time appears to slow to a glacial pace until it seems to stop altogether, and space seems to end, stretching into an infinite tautness. And then we will travel inside, down, all the way down into the deepest inner regions, where our familiar notions of time and space melt like snowflakes on a warm hand, where time, incredibly, seems to reverse its direction, where, from the ashes of a collapsed star, white holes are born. This is a travel tale. But it is a journey not across land or sea, but through the landscape of ideas. It is also the tale of an ongoing adventure, a scientific quest happening right now, in our time. As at the beginning of any journey, I am not sure where it will take me. At that first smile, we can't ask where we are going to live together, but I have a flight plan in mind, a map drawn in the faint ink of theory and calculation. We will journey together to the edge of the horizon. We will feel the pull of its immense gravity. And then we will enter. We will go down, down through the warped heart of the collapsed star till the very bottom. And then we will cross it and break through, like Alice stepping through the looking glass, to emerge on the other side. into the startling, brilliant light of a white hole. There, in that reversed world, we will ask what it means for time to be reversed, for the past to become the future, before re-emerging, blinking, to see the stars again, our familiar stars scattered across the sky, after a time that has lasted for just a few seconds for us, but also for the universe we left behind, perhaps millions or even billions of years. Or maybe, just maybe, for the time that it takes to listen to this voice, to follow this story as you drift into sleep. Are you coming with me? Marseille. The memory is vivid, etched in my mind with the clarity of the Mediterranean sun. Hal is in my study, standing in front of the blackboard, which is covered in the ghosts of past equations, a palimpsest of thought. I am sitting in the big reclining chair, my elbows on the desk, eyes fixed on him, trying to grasp the shape of the idea he is carefully unfolding. Coming through the window is the clear, dazzling light of the south of France, a light that seems to make everything sharper, more real. This is how my adventure with white holes begins. Hal is American. He has a natural gentleness that tempers the sheer, startling brilliance of his ideas. Today, he is a respected college lecturer. At the time of this memory, he was still a student, yet he possessed a quiet confidence. Kind, precise, with the composure and the calmness of someone very mature for his years. He is trying to tell me something I don't quite understand, a whisper of a concept that is just beyond my grasp. It is an idea about what could happen to a black hole, not during its long, quiet life, but at the precise moment that its life comes to an end. I remember his words, spoken with that calm deliberation. Einstein's equations do not change if we reverse time, he says. To have a rebound, we just reverse time and paste together the solutions. I'm confused. The words are simple, but the implication is monumental. I feel a friction in my mind, the resistance of old assumptions. And then, all of a sudden, like a lock turning, I see what he means. The space he opened with his words is flooded with light. Wow. I'm Italian, you see. There is no calmness in such moments. The idea rushes in, and my heart beats faster. I jump up from my chair and go to the blackboard, grabbing a piece of chalk. I make a drawing, a diagram of spacetime, a collapsing funnel meeting an expanding one, a bridge. He thinks about it for a moment, his head tilted slightly. Yes, he says. That's more or less it. And I, carried by the momentum of the revelation, add, it's a black hole that quantum tunnels into a white one on the inside, and the outside can stay the same. He thinks about it a bit more, a longer pause this time, the true measure of a scientist weighing a new reality. Yes, I don't know, he says finally, with beautiful, perfect intellectual honesty. What do you think? Might it work? It has worked. At least, the mathematics has. The theory stands. 9 years have passed since that conversation, in the clear, bright light of Marseille. I have continued, with my students and my colleagues, to walk down the path that opened up that day. We have continued to work on the hypothesis that black holes can transform into white ones. It's an idea that seems quite beautiful to me, not just for its mathematical elegance, but for its sense of cosmic completeness, of symmetry, of rebirth. The idea that I want to tell you about here, I do not know if it is correct. This is the nature of the frontier. I do not even know if white holes actually exist in our universe. We now know a great deal about black holes. We see their effects, we capture their shadows, we hear them merge, but no one has ever seen a white hole, yet. When I was studying for my doctorate in Padua, my professor of theoretical physics was a wise and witty man named Mario Tonin. He taught us the deep, elegant architecture of the quantum world. And he used to tell us, with a twinkle in his eye, that he thought every week the good Lord reads Physical Review D Top, the celebrated physics journal, where we publish our new ideas. Whenever he came across an idea he liked, Shazam! He would put it into practice, rearranging the universal laws accordingly, just for the beauty of it. If this is so, dear Lord, I would be grateful if you could arrange this. Make it so that black holes end up becoming white holes. I read the preceding lines. The story of my first encounter with white holes. I want to explain everything in order, step by step, without haste. What kind of objects Hal and I were talking about that day? What we know for certain, what we infer from our equations, and what remains shrouded in mystery. What the problem was that we were trying to unravel, a paradox that had puzzled physicists for decades. What Hal's idea was, exactly, and what its profound implications are. What it truly means to reverse time, it is nothing complicated, as you will see, and what it means for time to have a direction at all. This, perhaps surprisingly, is the complicated part. If you follow me, I'll take you on a journey. I will be your guide. We will travel to the edge of a black hole's horizon. We shall not be afraid. We shall enter it, go down to the bottom, into the heart of spacetime's greatest storm. We shall cross through the quantum foam and emerge into a white hole where time flows backwards. Then we will go up and out until we see our own familiar stars again, perhaps in a future so distant it would seem like a different universe. Let's start the journey toward white holes. Actually, no, that is not quite right. We must begin our journey not by seeking the white, but by understanding the black. To understand what a white hole is, what this strange, radiant object could be, we need a clear idea of what a black hole is. What is it, this object of myth and science, this ultimate prison of light? The first to go wrong was Einstein himself. In 1915, after a decade of what he called mad and desperate work, a period of intense intellectual struggle that pushed him to the limits of his genius, Albert Einstein published the final, beautiful equations of his most important theory, a theory that is studied today in every university in the world: general relativity. It was his masterpiece, a new way of understanding gravity not as a force, but as the very curvature of the fabric of reality. Just weeks after its publication, as war was tearing Europe apart, he received a letter from a young colleague, Karl Schwarzschild. Schwarzschild was a lieutenant in the German army at the time, stationed on the Eastern Front, calculating artillery trajectories amidst the chaos and carnage of World War I. In a few short months, he would lose his life, not to a bullet, but to a rare autoimmune disease contracted in the harsh conditions of the front. The letter he sent to Einstein from that place of death and destruction concludes with these beautiful, haunting words. As you can see, despite the incessant artillery fire, the war has treated me kindly enough to allow me to briefly walk away from all that, and to be able to take this walk on the land of your ideas. A walk on the land of your ideas. What an incredible testament to the power of the human mind, to find solace and beauty in abstract thought while surrounded by the ugliest expressions of human folly. Schwarzschild's walk on the land of Einstein's ideas during a pause in the fighting on the Russian front, among the corpses of young Germans and Russians slaughtered by the human stupidity that raged then as it rages now. What can be more stupid than to die for a line on a map? Resulted in an exact solution of the equations that Einstein had just published. These equations had cost Einstein dearly. You can trace his struggle through a sequence of his articles from those years, each presenting a different, slightly incorrect version of the equations. All wrong. But in 1915, finally, they were correct. They were perfect. These are the equations that convinced physicists to completely revise their ideas on the nature of time and space. They showed that clocks go faster in the mountains than they do in the plains, that the universe itself is expanding, that there are waves of space, ripples in reality, and so on. They are the equations that we use today for studying the cosmos, from the birth of the universe to the death of stars. Perhaps they are the most beautiful equations in all of physics. In the course of these pages, we will have a close but uneasy relationship with these equations. They will serve as our guide, like Virgil to Dante and Asterix the Divine Comedy, because they encapsulate the best understanding that we have today of space, time, and gravity. They are our tool for understanding, our map of the territory. They tell us what to expect at the edge of a black hole and inside it. They also tell us what white holes are. They show us a route through these strange, alien territories. And yet, the whole point of the story I am about to tell is to go and see what happens, where these equations no longer work, where they cry out in protest and predict infinities, where they tell us they have reached their limit, where it is necessary to abandon them. This is the soul of science. It is not a collection of settled facts, but a continuous process of questioning, of pushing our guides until they falter so we can find a new path. In the middle of our journey, we must abandon the reassuring guidance of these equations and be led by something else, a different kind of intuition, a quantum intuition. Just as Dante, in the middle of his journey, leaves Virgil behind and is captivated by something more alluring, by the light in Beatrice's eyes. Let's return to Schwarzschild on the frozen front. The solution that he announced in his letter to Einstein is also in all university textbooks today. It describes what happens to space and time around a mass, around the Earth or the Sun, for example. The Earth's and the Sun's gravity causes space and time to bend. I will soon try to explain what this strange phrase, bending space-time, truly means. It is this curvature of space and time that causes bodies to fall toward the Earth and the planets to orbit in their graceful ellipses around the Sun. It is the underlying reason for the force we call gravity. The question studied by Schwarzschild was how things are moved by the effect of gravity around something heavy, such as the Earth or the Sun. This is the same question Isaac Newton had studied so brilliantly 3 centuries earlier, opening the path to modern science. Einstein and Schwarzschild correct Newton, improving on his predictions of how things move around masses, adding tiny, almost imperceptible refinements. But the solution found by Schwarzschild does not give just some small correction to the movements of the planets. Buried deep within the mathematics, it also predicts something radically new and strange, terrifyingly strange. It predicts that if a mass is extremely concentrated, if it is crushed beyond a certain critical point, it generates a shell around itself, a spherical surface where everything we hold to be normal becomes bizarre. On this surface, clocks, which always slow down in the vicinity of any mass, would come to a complete stop. Time, as we know it, would freeze. It would no longer flow. Space, for its part, would elongate in the direction of the mass, stretching like a long, dark funnel. And on this absurd spherical surface, the stretching would become a tear. The points immediately within it would already be infinitely distant. It is as if space itself were being pulled apart at the seams. Time stopping, space tearing. This sounds like mathematical nonsense, a pathological breakdown of the theory, not a description of the real world. Einstein, understandably, concluded that this was precisely the case. This absurd surface could not exist in reality. It was a flaw in the map, not a feature of the territory. In fact, if we do the math, we see that for this surface to be formed, it is necessary to crush a mass to a ridiculous, almost unimaginable extent. To form such a surface around our Earth, for instance, we would need to crush the entire planet, all its oceans, its mountains, its molten core, down to the size of a ping-pong ball. Absurd. All of this, Einstein concluded, was without interest for the physical world. You simply cannot concentrate a mass so much as to arrive at the point where this bizarre shell is formed. He was wrong. In this, he did not have enough faith in his own equations. He did not have the courage to believe the strange and wonderful implications of his own theory. We now know better. Masses, as concentrated as this, do exist. As a matter of fact, there are billions upon billions of them scattered like dark jewels across the heavens. They are what we call black holes. Astronomers have observed them, charting their locations and measuring their properties. They vary in size from a few kilometers in diameter to truly colossal, as big as our entire solar system, or even bigger. There may also be small ones, as small as a ping-pong ball, and even extremely small ones, weighing no more than a hair. Primordial remnants from the dawn of time, but for now, we have not seen them. For now. Most of the black holes we have identified in the sky originated from the death of great stars. They were once large, brilliant suns, so heavy that they would have collapsed on themselves instantly had it not been for the fierce fire burning in their cores. Stars burn the hydrogen of which they are made, fusing it into helium in a continuous, controlled nuclear explosion. The tremendous heat produced by this cosmic furnace generates an outward pressure that perfectly counterbalances the star's own immense weight, preventing it from being crushed by its own gravity. In this state of delicate equilibrium, a star continues to live and burn for millions, or even billions of years. But nothing is forever. In the end, the hydrogen fuel in the star's core is consumed and turned into helium and other heavier elements, ashes that burn no more. The star is like a car that has run out of fuel. The fire dies down, the star's temperature drops, its outward pressure fails, and its own immense weight begins to prevail. The star is crushed by the relentless effect of its own gravity. The gravitational force in a large star is tremendous. Not even the hardest rock, not even diamond, could withstand its pressure. Now that there is no longer anything to prevent the star from collapsing in on itself, it falls. It collapses all the way down, shrinking catastrophically until its surface passes through its own horizon. A black hole is formed. In 1928, long before this process was understood, the Bell Telephone Company hired a young physicist named Karl Jansky to study the strange noises that were disturbing their new transatlantic radio communications. Jansky, a meticulous and curious engineer, built a rudimentary but very large directional antenna to hunt for the source of the static, a bizarre-looking grid of metal rods mounted on a set of 4 Ford Model T wheels, allowing it to rotate in any direction. His colleagues, with a touch of amusement, dubbed it Jansky's merry-go-round. With this strange antenna, Jansky began to patiently record all the radio signals he could find: the sharp crackle of distant thunderstorms, the hums and buzzes caused by other man-made radio antennae, and so on. But among the others, a curiously regular signal was detected, a faint but persistent kind of hiss that was captured at every full turn of the merry-go-round. Jansky's sister tells how their father raised his children, encouraging them to investigate everything. And so Jansky investigated the hiss for more than a year, with the patient tenacity of a true explorer. At first, he noticed that the hiss increased and decreased in intensity every 24 hours. This seemed simple enough. Jansky thought it could be coming from the sun, which passes over us once a day. But the universe is subtle, and the devil is always in the details. Continuing to monitor the signal with greater precision, Jansky noticed that the period was not exactly 24 hours. It was a little less, 23 hours and 56 minutes. This meant the stronger signal was not arriving at the same time of day. It kept sliding earlier and earlier by about 4 minutes each day, like a clock running just a little bit too fast. This was strange. It could not be the sun. The sun does not run faster than the days. Stars do. A fellow astronomer pointed out to Jansky that 23 hours and 56 minutes is not the solar day, but the sidereal day. It is exactly the period it takes for the distant stars to appear to rotate around us. The 4-minute difference comes from the fact that the Earth is also orbiting the Sun, so it has to rotate a little extra each day to catch up to the Sun's position. The mysterious radio signal, therefore, could only be coming from the stars. The direction was now easy to find. It originates from the part of the sky toward which the antenna is pointed when the signal is strongest. By consulting a star atlas, he located the source. The hiss was coming from the constellation of Sagittarius, from the very center of our own galaxy, the Milky Way. This was such sensational news that it ended up in Asterisk, the New York Times, under the headline, "New Radio Waves Trace to Center of the Milky Way." On May 15, 1933, with millions of Americans listening in on their home radios, NBC broadcast Live the Hiss Coming from the Stars, along with an interview of Jansky. "Good evening, ladies and gentlemen," the announcer's voice crackled. "Tonight, we are listening live to radio signals received from outside the solar system, from somewhere among the stars." Jansky then explained to the audience that the signal was coming from the center of the galaxy. The announcer commented that the strength of a signal reaching us from 30,000 light-years away must be immense, and that it must be millions of times more powerful than any radio station on Earth. 5 days earlier, in the Opernplatz in Berlin, the Nazis had staged the biggest of their infamous book burnings. Among the thousands of texts turned to ash were works by the poet Vladimir Mayakovsky and books by and about Albert Einstein. 90 years later, thanks to the very ideas in those burned books, we know what the mysterious whistle heard by millions of Americans really is. It is the radiation emitted by incandescent matter, superheated gas and dust, that whirls furiously at nearly the speed of light before taking its final plunge into a colossal black hole at the center of our galaxy. A black hole 10 times as big as the entire orbit of the Moon around the Earth, with a mass 4 million times that of our Sun. I am on my 3rd revision of these pages, and just today, astronomers have released an image of precisely this black hole. The image, a triumph of global collaboration, shows the glowing ring of burning material that whirls around the hole, generating the very same radiation captured nearly a century ago by Jansky's humble antenna. Here it is, a donut of fire surrounding a circle of pure blackness. I am moved intensely by this image. I have studied black holes all my life, dreamed of them, worked through their equations, without knowing for certain if they truly existed as physical objects. And now, here they are. Here is the visual evidence, something I could never have imagined when I was a university student, utterly charmed by these impossible holes in space. 20 years ago, there were still many serious scientists who doubted the existence of black holes. When in January of 2000 I moved from the United States to France to take up a new post, my new department head asked me, a little skeptically, "You don't really believe that black holes actually exist, do you?" Now, he has changed his mind. And this is not meant as a criticism of him. It illustrates, rather, the profound beauty of the scientific process. There is nothing wrong with changing your mind when presented with new evidence. In fact, it is essential. We are all still learning. The best scientists are the ones who change their minds most often, as Einstein himself did throughout his life. In the image before us, the actual black hole, or rather its horizon, as we call the bizarre surface enclosing it, is the small, dark disk in the very center, nestled in the heart of the fiery matter that revolves around it like water spiraling down a drain. This horizon is our way in. We approach the threshold, this silent, invisible boundary we call the horizon. What happens at the horizon of a massive black hole, just past the material that swirls so violently and becomes so incandescent that its whisper can be detected by a grid of iron rods 30 million light-years away? It took decades of fierce debate and brilliant insight to understand what truly happens on the horizon. Einstein was not the only one to have misunderstood it. Physicists remained deeply confused for a very long time. Only in the second half of the 20th century did we begin to untangle the paradoxes and clarify the view. And even today, there are quite a few colleagues in my field who get confused about them, and this, I confess, is meant as a gentle criticism. Let's go and see for ourselves. In a work of fiction called The Dream, Johannes Kepler, the great 17th-century astronomer who first understood how the planets move in ellipses around the sun, describes how his mother, a healer accused of witchcraft, took him on a journey around the solar system, as if on a flying broomstick, to show him the celestial dance from a different perspective. Kepler's mother was indeed tried for witchcraft, and just in case you are wondering if she really was a witch, at her trial, defended passionately by her son, she was acquitted. Kepler, perhaps thanks to the imaginative spirit of his mother, the accused witch, wanted to go and see. To go and see. This is the fundamental impulse of science. To go and look where we have not been before, by using every tool at our disposal, logic, reason, mathematics, but also intuition and, most importantly, imagination. To travel around the solar system, to journey to the heart of atoms, to explore the intricate pathways inside living cells, to map the convolutions of the neurons of our own brain, to travel far into the past, and to venture beyond the horizon of black holes. To go and see with the eyes of the mind. On Earth we call horizon the distant line beyond which we cannot see, the line where the sea seems to meet the sky. If we get on a ship and sail toward it, we can cross that line, we can go beyond the horizon, and when we cross it, nothing particular happens. The water does not change, the air does not change, except that we vanish from the view of anyone watching us from the shore, without this involving anything special happening to the ship, perhaps a small party on board, in some maritime traditions to celebrate the passage. And here is the first surprising thing, the first deep insight we must grasp. The same is true for the horizon of a black hole. Traveling in a spaceship, we can get as close to the horizon as we like. We can reach it. We can cross it. And at the moment of crossing, nothing special happens. Nothing at all. Our watches continue to tick at their normal rate, 1 second per second. The distances around us in our spaceship continue to be the same. The laws of physics are unchanged. Only, just like the ship that sailed over the sea's horizon, we can no longer be seen by watchers from afar. We are now beyond their horizon. If we try to signal our friends back home by sending a pulse of light, a message, back toward the outside, that ray of light cannot escape. It is trapped, caught in the current of space-time, and pulled inward with us. We can no longer reach our distant friends. Inside the horizon, the pull of gravity is so overwhelmingly strong that it traps everything, even light itself. Why, then, does the original solution found by Schwarzschild indicate that at the horizon, clocks stop and space breaks down, confounding Einstein and so many others for so long? If you can cross the horizon and find everything perfectly normal there, is Schwarzschild's solution wrong? It is not wrong. It is just written from a specific point of view. It is written from the perspective of someone who remains distant, looking at the horizon from the outside. Schwarzschild's solution is like a particular kind of geographical map of the space outside the horizon. With geographical maps of our spherical Earth, and this is well known, something peculiar always happens when we try to represent the curved surface on a flat piece of paper. Let's take a common map of the Earth made up of two disks, one for the northern hemisphere and one for the southern. The equator, on this map, appears as the circular edge of both disks. It seems to be the edge of the world. In reality, of course, the equator is not the world's rim, and nothing special happens there, apart from the heat and humidity. The surface of the Earth is not flat, so it does not fit perfectly into just one flat map. But the world certainly does not finish at the edge of the map. Spacetime around a black hole is not flat either. It is curved. And similarly, it does not fit perfectly into a single mathematical map. It does not end at the edge of Schwarzschild's solution. This is what happened to Einstein and all the others. They interpreted the solution badly, like someone looking at that two-disc map of the Earth and deducing that the world physically ends at the equator. This mistake was made by dozens of outstanding scientists for decades. And there are still some scientists, even among the big shots, who still make it. How do we know that it is a mistake? After all, none of us has actually gone there yet to witness in person what happens at the horizon of a black hole. None of us has gone there, but we have the theory. The very same set of equations of general relativity that yields the Schwarzschild solution also allows us to compute what a falling observer would experience as they approach and cross the horizon. Working this out is not even that difficult, mathematically. I sometimes set it as an exercise for my graduate students when I teach general relativity, but it took a long time for someone to think about doing it in the first place, and even longer to understand what it truly meant. This someone was David Finkelstein in 1958. I was just 2 years old at the time. Finkelstein was a vastly cultured scientist, a deep and daring thinker with interests that ranged from politics and art to music and philosophy, as well as science. He left us not long ago, in 2016. I was lucky enough to meet him in the last years of his life, with his long, flowing prophet's beard and a manner that was somehow both laid back and deeply serious. He was one of those rare scientists who do not just solve problems, but open up entirely new vistas, new pathways for thought. We will encounter him again later in this story. In 1958, Finkelstein published a beautiful, brilliant article in which he finally clarified the true nature of the black hole horizon. The title of the article is Past-Future Asymmetry of the Gravitational Field of a Point Particle. It sounds technical, and it is. But keep this title in mind, because the idea it expresses, this asymmetry between past and future, will be the keystone to our entire story. Finkelstein's calculation shows, with mathematical certainty, that if we approach the horizon and go beyond it, our watches do not slow down, and nothing strange happens to the space around us, just as nothing peculiar happens to a ship when it crosses the line of the horizon on the ocean and disappears from our view. So why do watches appear to stop in Schwarzschild's solution? Why does time seem to freeze? Because Schwarzschild's solution describes what happens there as seen from afar. From a great distance, all timepieces do appear to slow down and stop as they approach the horizon, and there is no contradiction between these two perspectives. They are both correct. Let's imagine that we are traveling through a series of remote countries, where the postal service gets progressively slower and slower, and that we are sending a letter home to our father every single day to let him know we are safe. At the beginning of our journey, our father will receive a letter from us every day. But as we travel into regions with slower mail, he will begin to receive our letters at lengthening intervals. For him, it will seem as if our life has slowed down. Initially, he will get news of our day from us every day, but then he will have to wait several days, and eventually even weeks, just to learn about a single new day of ours. For him, watching from home, it is as if our time has slowed to a crawl. If we finally reach a vast, remote desert from which there is no mail service at all, he will receive only the very last letter we wrote before entering that desert. That last letter will arrive a long, long time after we sent it. For our Father, the edge of that desert is therefore the place where, for him, our time stops. It is the horizon beyond which he can no longer see us. He will continue to visualize us there, frozen in that last moment, at the desert's edge, forever about to take that final step. Something very similar happens if we fall across the horizon of a black hole. If our Father watches us with a powerful telescope as we go toward the horizon, he sees the ticking of our watch getting gradually, progressively slower. This is because as we get closer to the horizon, the light from our watch takes longer and longer to struggle away from the immense gravity and reach him. The light lingers near the horizon, held back by the curvature of spacetime, before being able to escape. If our Father continues watching, he will see the moments of our life slowing down until they come to a complete halt. He will see us frozen in time with the final tick of our watch just before we cross over. In the desert, or beyond a black hole's horizon, we continue our journey. We continue to exist as normal. But our Father, waiting patiently back home, will no longer receive anything from us, no new letters, no new light, however long he waits. Time, in short, does not come to a stop for those who have crossed the horizon. It is only for those looking from afar that what happens near the horizon appears dramatically, infinitely slowed down. The analogy with the letters sent while approaching the desert is a good one. It helps to build intuition. But it is good only in part. There is a crucial difference between the trip to the desert and the trip to the horizon of a black hole. If, instead of going all the way into the desert, we were to turn back and return home to embrace our Father again, the hours that will have passed since we last saw him would be the same for us both. If he is a year older, we will also be a year older. Our watches would still be synchronized. The same does not hold true for the temporal distortions in the vicinity of the black hole's horizon. These are real and concrete in the following profound sense. If we approach the horizon, linger in its powerful gravitational field for a while, and then use our powerful rockets to turn back and return to our Father, the time that has elapsed for us, between last seeing him and embracing him again, will be shorter than the time that has passed for him. He will have aged more than we have. If a year has passed for us on our journey, we might return to find that 10 years or 100 have passed for him. This is not a perspective effect. It is a real physical distortion of the passage of time caused by gravity. Where gravity is strong, time itself actually passes more slowly than where it is weak. Time, we are forced to conclude, passes at different rates in different places. This is precisely what we mean when we say that space-time is curved. It is not just a metaphor. There is literally less time near a massive object. There is less duration in the vicinity of the horizon, and this fundamental fact bends the fabric of space-time, the way taking away a section of stitching from a piece of knitted fabric would cause it to pucker and bend. In sum, then, close to the horizon, time slows in two distinct ways. It slows in the sense that anyone observing us from afar would see us moving in extreme slow motion. And it also slows in the sense that if we were to turn back, more time will have passed for those who remained at a distance than has passed for us. In another sense, on the other hand, time does not slow at all. For us, who are there at the horizon, no slowing is felt. Our hearts beat at their normal rate. Our thoughts flow as they always do. For us, time passes normally. Perhaps, dear reader, it has occurred to you at this point to ask a very natural question. Which of these different times is the real one? The time of the person at the horizon, or the time of the person watching from a distance? The answer, and this is the heart of Einstein's revolution, is that neither of them is the single true time. The question of which time is the true time is a meaningless question. It is like standing on the earth and asking which direction is truly up and which is truly down. With respect to each location on the planet's surface, that location is up, and all the others are in various directions, down or sideways. Every place on Earth determines a different local up and down. The difference is only a question of perspective. In precisely the same manner, every place in the universe has its own local time. Different places can send signals to each other, like the ancient whistle sent to us from the black hole at the center of our galaxy, but time passes at unequal rates in different places, and no single one of these times is any truer than any other. In other words, the slowing down of time in the vicinity of the horizon is something that regards only the relation between how time passes in different places. It is only in relation to the time of a distant observer that time appears to stop or is physically slowed down at the horizon. The world, then, is not a single clock ticking away a universal history. It is a vast, intricate tapestry woven from these relations between countless local times. There is no universal time. Temporality is the network formed by the many local times and the possibility of exchanging signals between them. From close up, the horizon is a perfectly normal place. From a distance, it is the place where time stops forever. This is the profound truth that David Finkelstein understood. Finkelstein, with his wide-ranging mind, once wrote an article about an engraving by the renowned Renaissance master of perspective, Albert Dürer. The engraving, titled Melancholia I, is a complex, mysterious work charged with dense layers of symbolism. It depicts a winged, melancholic figure surrounded by objects of science, art, and geometry, staring into the distance with a look of profound, thoughtful sadness. I think it is no coincidence that the first person to truly understand the horizon of black holes was not a pure mathematical genius, but someone with the breadth of spirit to write about Albrecht Dürer and the discovery of perspective in Renaissance art. The Renaissance, after all, discovered the art of perspective in painting. It discovered that our entire access to reality is perspectival. According to Finkelstein, the deep ambiguity of Dürer's engraving reflects and represents this unavoidable ambiguity between different perspectives on the world. In his reading, the engraving stages the melancholy of those who vainly attempt to reach an absolute, single, God's eye view of truth and beauty. The impossibility of obtaining the absolute, for Dürer and for Finkelstein, is the source of our melancholy. It is not the case for me. On the contrary, this relativity of everything, this lack of a solid, absolute foundation, seems to me to be the source of a gentle dizziness. The dizziness of lightness, of the intoxicating inconsistency of that delicate, shimmering texture that is the reality of which we are all a part. We have access only to perspectives. Reality is perhaps nothing other than the sum total of all possible perspectives. There is no absolute. We are limited. We are impermanent. We are nodes in a network of relationships. And precisely for this reason, to live, to be, as we do, is so light and so sweet. So here we go. The moment has arrived. We are at the edge of the horizon. Let's cross it. Thanks to Finkelstein, we are not afraid that the world will end here. It is not the first time in human history that dark, forbidding advice, "Abandon all hope, ye who enter here," turns out to be unduly threatening. We enter, then, with the courage of those who launched themselves toward the unknown. We enter with the voice of Ulysses in our ear, as Dante imagined him speaking to his men. Do not pass up the chance to experience, beyond the sun, the world where no one lives. Consider your origin. You were not made to live like brutes, but to pursue virtue and knowledge. And like the companions of Ulysses, on this mad flight, we'll make wings of our oars. We are now within the black hole. We have passed into the secret things. With a good map of the stars, which, surprisingly, remain visible from the inside, though warped and distorted, we are able to recognize that we have crossed the threshold, the point of no return. We are beyond the boundary from which we can no longer send letters home. It is too late now to stop and turn back. Beyond the horizon, where not even light can fight its way out, we have even less chance than light of doing so. However many powerful rocket engines we might have taken with us on our ship, there is now no way of avoiding a continuous fall toward the center. In order to come out again, we must take another path, with a little attention, and by observing our surroundings, we can also account for the fact that we are inside a black hole just by looking around. Here, inside, space is still spherical, just like it is outside, arranged in nested spheres around the center of gravity. But outside, with powerful enough rockets, we can move away from the center, upward, so to speak, toward larger and larger spheres. Inside, on the contrary, whatever we do, however we fire our rockets, we will find ourselves in ever smaller, ever-constricting spheres. The inward pull of gravity, the very current of space-time itself, is so strong that we can do nothing to impede our descent. Like Dante and Virgil descending through the concentric circles of the inferno, we go down. The geometry of the space inside a black hole, down there in the blind world below, is actually surprisingly similar to that of Dante's Inferno. Think of a funnel. A very, very long funnel. At any given moment, the interior of the black hole can be imagined as this long, tapering funnel. The older the black hole, the more elongated and stretched its interior. The interior of a very old black hole might even be millions of light years in length, a vast, tube-like universe hidden inside a tiny portal. The image below illustrates how we can think of the space inside a black hole at a single instant of time. However enormous it might be, the length of this funnel is not infinite. At the very bottom, there is still the remnant of the star that, by collapsing in on itself, gave rise to the hole in the first place. Unlike Dante's Inferno, however, which as far as we know stays the same for eternity, the funnel here is dynamic. It lengthens and narrows with the relentless passage of time. In order to illustrate this fact, this constant evolution, the drawing below shows a succession of funnels, each representing the interior of the black hole at a successive moment in time. Following the strange habit of physicists, the drawing shows a sequence in which time runs from the bottom to the top of the image. I do not know why this is the convention we have adopted. Perhaps we have borrowed it from geologists, who always draw the past below, because the oldest layers of rock are the deepest underground. The drawing must therefore be read from the bottom upward. As you go up into the future, the tube that represents space lengthens and narrows. If we go down into the black hole, falling with gravity, at each moment we are at a point in this ever-changing funnel, going farther and farther down, into a tube that gets progressively longer and tighter around us. This is the shape of space inside a black hole, an endless abyss, dark and deep and nebulous it was, that gradually constricts around us as we fall, without our ever being able to reach the bottom, where the star that gave rise to it in the first place has fallen long ago. How do we know all this, you might ask? How can we speak with such confidence about the shape of the interior of a black hole if no one has ever been there to see it and returned to tell the tale? We know it because the inside of a black hole, up to a certain point, is fully and beautifully accounted for by Einstein's equations of general relativity. Until something happens to create any doubt, until the equations themselves tell us they are failing, we have no reason not to trust in them. We trust them because their predictions, as spectacular and unexpected as they were, have so far all turned out to be correct, from the bending of starlight to the existence of gravitational waves. These equations are our faithful guide. They are our good Virgil for this part of the journey. They are our Duke, Lord and Master, showing us the way down, farther and ever farther down into the blind world. Sooner or later, however, even the best of guides no longer suffices. Sooner or later, something always happens that causes us to doubt our maps, our theories, our most trusted equations, or, as the great Chinese master of Chan Buddhism, Linji Yixuan, has it, in a phrase of profound wisdom, if you meet the Buddha on the road, kill him, meaning, if you want to find truth, you must be prepared to abandon even your most cherished beliefs, even your enlightened masters. Deep down where we are falling, inside this tightening tube of space, we eventually reach regions where the distortion of spacetime becomes extremely, unimaginably strong. Here, in this zone of ultimate pressure, we expect new physical phenomena to intervene. We expect quantum effects to come into play, as they always do in such extreme conditions. Einstein's equations of general relativity do not take account of such quantum phenomena. They are classical equations. They ignore the granular, probabilistic nature of the world at its smallest scales. In these extreme regions, therefore, those elegant equations no longer serve us. Our guide has fallen silent. We have lost our Virgil. In effect, we are certain that at some point Einstein's equations must fail, because if we continue to rely on them without correction, they go mad. They predict that the geometry of space-time will reach an infinite distortion, that the curvature will become infinite, and here they simply no longer work. The value of the variables in the equations becomes infinite, a mathematical sign of breakdown, and we cannot compute any further. The theory, our staunch and faithful guide, does not help us anymore. We call these regions, these points of infinite density and curvature, these spikes and cusps and folds in reality, singularities. But once again, the devil is in the details. Let's look very closely at exactly where the equations stop working. Pay careful attention now. This is a subtle point, but it is the detail that has caused the most confusion among scientists for half a century. It still confuses many, even some of the very best. It was clarity on this single subtle detail that allowed Hal and me to escape the impasse and see a new way forward. It may seem natural to think that the strange things, the infinities, must happen at the bottom of the funnel, down there in the geometric center of the black hole, where the star originally collapsed. But this is not the case. In the center of the funnel, there is only the falling remnant of the star. We are not yet in the territory of the singularity. Here, in the center, Einstein's equations still work just fine. How can this be? If we fall into a black hole that is very old, one that formed billions of years ago, has the star not finished its fall a long, long time ago? Has a vast amount of time not passed since it collapsed? A star that collapses on itself should be crushed to a point in a very short lapse of its own time. So how can it still be there, still in the process of falling after all this time? Time. It is always the crux of the matter. The elasticity of time is the key. A long time for one observer does not mean a long time for another. A long time for us, watching from the outside, does not mean a long time for the star itself. Down there, at the bottom of the gravitational well, time has slowed down to an almost unimaginable degree. Outside, in the wider universe, billions of years may have passed, while down there, for the collapsing star, just a few fractions of a second have ticked by. The star is still falling at the bottom of the long, stretching, narrowing funnel because, in its own proper time, no more than fractions of a second have passed since its collapse began. So the zone where the distortions become infinite, where the equations of Einstein break down, the truly interesting zone, is not there, in the center. So where is it? It is in the future. It is not a place, but a moment. It is in what happens after the interval of time depicted in the last image. It is what awaits the falling matter, and us, at the end of the journey down the tube. It is in the gray area of the image below. As the diameter of the funnel of space narrows, the cylinder becomes more and more curved, like a sheet of paper that is being rolled tighter and tighter. The more the funnel is narrowed, the greater the distortion of spacetime. When this curvature reaches a fateful, critical value we call the Planck scale, the scale where we expect space and time themselves to be seriously affected by quantum phenomena, we enter the region where these quantum phenomena become dominant and imply that Einstein's equations are violated. This is the gray zone in the image above. If we ignore these quantum phenomena and foolishly trust in Einstein's classical theory all the way down, the equations predict that the crushing of space continues until a final catastrophe occurs. The long, thin tube of space becomes ever longer and thinner until it is squeezed into a single line of infinite density, crushing us and everything else with it. And then that's it. Space is collapsed. Time is finished. We hit a wall. If we go along with Einstein's theory to its bitter end, time itself ends here. The story stops. So the region of the singularity, the quantum region, is in our future as we fall. It is where the tube of space is squeezed into a line and becomes infinitely long. It is not in the center of the ball that is the black hole, as, alas, so many continue to think. In the center, there is only the still falling star. This critical misunderstanding is a main source of the decades of confusion about the ultimate fate of black holes. To understand what happens in a black hole, in other words, we should not think of a static cone with the singularity sitting at its central point. We need to think of it as a dynamic, long tube with the star that generated it at the bottom. This tube gets longer and thinner with time, and in the future, it is squeezed into a line. The singularity is not at the center, it is after. It is the end of the fall. This is the key to the entire story. Falling in the black hole, that is where we end up. That is the last depth and the darkest lair, and the farthest from heaven which encircles all. With that, we have reached the quantum zone. So what happens now? Einstein's equations, our Virgil, our guide, The most beautiful equations in all of physics, the ones that have accompanied me throughout my scientific life. They are no longer enough. Now we have no guide, just as Virgil left Dante at the summit of purgatory. He had gone. Virgil had gone. Virgil, the gentle father to whom I gave my soul for its salvation. What happens next? This is the question Hal and I were discussing on that clear, sunlit afternoon in Marseille. We have arrived at that summer's day in my study, when, after months of attempts, errors, false leads, and discarded ideas, Hal suggested reversing time and linking two spacetimes with a quantum tunnel. What did he mean by this? He meant to suggest what might lie beyond the singularity, beyond the end of time predicted by general relativity. The suggestion was based on the simplest, most intuitive of analogies. The formation of a black hole is a fall. A star that has finished burning falls upon itself, crushed under its own weight. An object that enters a black hole falls. Space itself, the long tube in the drawings we have been considering, is crushed by falling upon itself. And what happens to things when they fall? They reach the bottom, and then, quite often, they bounce. If I drop a basketball on the ground, it falls, it deforms, it compresses, and then it springs back. It bounces and heads back upward. How does the basketball move after the bounce? Think about it for a moment. It moves as if a film of its fall were being played in reverse, backward in time. A ball that bounces is like a ball that falls, but seen starting from the end of the process and running backward. I have insisted on pointing out that the singularity of a black hole is not in the center. Rather, it is at the end of its fall. When the black hole, the collapsing star, and the space-time around it arrive at the bottom of their fall, in that gray quantum zone in the last figure, could they not simply bounce? Could the star and the whole of space-time not simply rebound and come back like a bouncing ball, as if time itself were reversed? A few months before my discussion with Hal, I had studied, together with my brilliant student Francesca, the possibility that a collapsed star could indeed bounce at the end of its fall. We christened this hypothetical bouncing star a Planck star, because the bounce is expected to happen at the Planck scale, the scale where quantum gravity becomes dominant. Could the full black hole, not just the star but the space-time it carries with it, actually bounce? What would we see if we were to imagine filming the full life of the black hole and then running that film backward? We would see a white hole. What, then, is a white hole? Remember that we knew about black holes long before they were ever observed. They were a valid mathematical solution of Einstein's equations. A white hole is the same thing. It is also a solution of Einstein's equations. We know about white holes in the same way we first knew about black holes, from the mathematics. Actually, a white hole is not even a different solution of Einstein's equations. It is the very same solution that describes a black hole, but with the variable for time reversed. It is the same solution with the sign of the time variable flipped from positive to negative. It is the same solution as seen backward in time. A white hole is simply what a black hole would look like if we could film its entire life and then run that film in reverse. Einstein's equations, like almost all the fundamental equations of physics, do not specify a unique direction for time. They do not, in their deepest structure, distinguish between the past and the future. If they allow a process to happen, they also allow that same process to happen backward in time. So if a black hole rebounds at the end of its collapse and retraces its previous route in time, like a basketball bouncing, this means that it must be transformed into its time-reversed counterpart, a white hole. Here is a drawing of how the internal space of the black hole can continue its story. When the collapsing tube of space enters the quantum zone, the gray area, it stops lengthening and narrowing. The crushing halt is dictated by the fundamental graininess of space itself. The bounce occurs, and the tube goes back, now shortening and widening, expanding outward. In a black hole, you can enter, but you cannot leave. The gravitational pull is too strong. In a white hole, the time-reversed version, the opposite is true. You can exit, but you cannot enter. It is an object that violently spews matter and energy outward. A film of things going into a hole, when run backward, shows things coming out of the hole. So anything that enters a black hole, a collapsing star, a curious astronaut, can cross the gray quantum zone, pass into the nascent white hole, and then come out again into the universe. Quite straightforward, no? Deceptively simple, perhaps. Is it really possible for this to happen? To pass from a black hole to a white hole, space and time must cross that gray zone in the figure, the quantum realm. This process violates Einstein's classical equations of general relativity. It may be only for a brief, fleeting moment, the instant of the rebound, but it is still a violation. But we expect Einstein's equations to be violated here. This is the very region where we know quantum effects must come into play. But do these quantum effects specifically allow for a rebound of this kind? The quantum physics of atoms, of electrons, of light, and of lasers are all well known to physicists. But here we are dealing with something far more fundamental: the quantum physics of space and time themselves. And this is precisely the reason that black holes and white holes interest me so much. I have spent my entire scientific life attempting to understand precisely these quantum aspects of space and time, trying to unravel the new conceptual structure needed to navigate a world where space and time are not smooth and continuous, but granular and probabilistic. It is my passion. I know the signs of the ancient flame. Down in the deepest bottom of the black hole, in that moment of ultimate crisis, I see her gleaming. I see the place where our current understanding breaks, and a new understanding might be born. For the most part, my work in theoretical physics has been to participate, with many brilliant colleagues, in the construction of a mathematical structure capable of dealing with quantum spacetime. The mathematical structure we have constructed is called loop quantum gravity. To understand what happens in the extreme regions of a black hole, where the quantum aspects of space and time dominate, and where the continuous, smooth canvas of space and time of our everyday experience no longer functions, this theory is needed. Here, in the heart of a black hole, we shall see if it works. Here, your worth will be tested. So what does quantum behavior truly mean? The simplest and most fundamental quantum property is granularity. At a small enough scale, all physical processes and quantities in nature manifest themselves in a granular way, in discrete packets. Light, for instance, when observed at very low intensity, does not behave like a continuous wave, but manifests itself in individual grains of light. We call these photons. When this basic idea of granularity is applied to space itself, it implies that there should be elementary grains of space, indivisible atoms of volume, of a finite size. We call these quanta of space. This means there are no arbitrarily small things. There is a fundamental lower limit to the divisibility of space. Space is a physical entity, and like any other physical entity, it is granular at its core. It is not an empty stage, but a physical dynamic object. Einstein's theory of general relativity and the mathematics of quantum theory, when combined, strongly imply this fact. The mathematics required to describe this granular space was developed years ago by the great English relativist Roger Penrose, who was awarded the Nobel Prize for his work on black holes while I was writing the first draft of this book. This mathematics as well was born of a simple, powerful analogy, a net. A net is a set of nodes connected by links. In this picture, the nodes represent the elementary grains of space. They are the quanta of space, just as photons are the quanta of light. But there is a fundamental and mind-bending difference. Whereas photons are particles that move within space, the quanta of space are the very grains that weave the net that is space itself. The links that join the nodes in this network indicate which quanta of space are adjacent to which others, thus defining a connected or spatial structure. Roger Penrose has called these structures spin networks. The term spin comes from the deep mathematics describing the symmetries of space, where the quantum property of rotation, or spin, plays a crucial and fundamental role. Here is a simple sketch of the relationship between one of these networks and the chunks of quantized space it describes. The second main feature of quantum phenomena, beyond granularity, is that the properties of things are not always definite or well-defined. A particle, for example, does not always have a precise position. Sometimes it can be nowhere in particular, disembodied and spread out like a wave, before suddenly materializing somewhere else when it is measured or interacts. It can leap from one state to another without passing through the states in between. One profound consequence of this leapy, probabilistic aspect of reality is the phenomenon known as the tunnel effect. This is the uncanny ability that things have to cross barriers that would be absolutely insurmountable if it weren't for the quantum world's strange rules. Imagine throwing a marble at a solid wall. Classical physics, and all of our common sense, tells us that it cannot possibly pass through the wall. In reality, the marble has a minuscule, but non-zero probability of simply appearing on the other side of it. This is the tunnel effect. It is called this because it is as if the marble could find an imaginary tunnel that allows it to cross through any barrier, no matter how thick or high. This was Hal's first idea. The inside of the black hole, upon reaching the point of maximum compression, is able to cross the zone forbidden by Einstein's classical equations, that gray zone in our figures, and jump by a magnificent quantum tunnel effect to the other side. The strange quantum properties of space and time themselves allow the interior of the black hole to leap beyond the singularity, the point where classical equations would have time stop forever. Quantum leaps are well known in physics. Since the early days of the quantum saga, the Danish physicist Niels Bohr realized that atoms emit light when their electrons jump from a larger orbit to a smaller one, instantly, without traversing the space in between. But here, in the heart of a black hole, the quantum leap we are contemplating is far more radical than a tiny particle hopping around from one location to another. Here, it is spacetime itself that jumps. The leap of spacetime is not a phenomenon that takes place in space and in time. How could it? It is a phenomenon that is neither spatial nor temporal. It is an instantaneous quantum transition from one entire configuration of space to another. Quantum transitions of this kind, these leaps from one geometry of space to another, are precisely what is described by the mathematics of loop quantum gravity. The familiar equations of ordinary quantum mechanics give us the probabilities that jumps from one configuration to another will occur for a physical system, like an electron, that exists in space. The equations of loop quantum gravity, our new tool, give us the probabilities of leaps from one configuration of space to another configuration of space. In crossing that gray zone where Einstein's theory predicts the end of time, time and space, as we know them, do not exist. So here we are, at the very heart of the matter. Here, the quantum properties of time and space flare up in all their strangeness and glory. I know the signs of that ancient flame. Here, we can finally cross what Einstein's theory defined as the edge of reality. We can pass to the other side. The equations of loop quantum gravity allow us to calculate the probability of this happening. This is the keystone. It is the keystone both of the scientific problem we are trying to solve, the ultimate fate of black holes, and of this journey we are on together. The leap beyond the end of time, a leap predicted by general relativity, can happen. It is predicted by quantum theory. Like all quantum leaps, it is a break, a rupture in continuity, a momentary fracturing of the smooth flow of existence. And yet, it is a fracture that is described by equations that we have, equations that we can write down and solve. The equations of quantum gravity describe a world that is more complex, more subtle, than a simple spatio-temporal continuum. Having ascended through the skies of purgatory and arrived at the very edge of the known universe, Dante loses his trusted guide, Virgil. But at that very same moment, filled with a profound and stirring emotion, I know the signs of the ancient flame. Asterisk, he sees Beatrice. A short while later, in a dazzling and complex play of looks between Dante, Beatrice, and the sun, Dante ascends from the earth to heaven, from the known part of the cosmos to the other, transcendent realm. Beatrice looks at the sun, and Dante looks into Beatrice's eyes, which reflect the sun's light. Beatrice upon the eternal wheels had fixed her eyes, and I on hers fixed mine. Following Beatrice's gaze, Dante himself is empowered to stare directly into the sun. He is flooded with a light beyond imagining. It seemed then that so much of the sky was lit. There is nothing else in that moment of transition in the leap but a lake of light, and suddenly it seemed that a sun was added to the sun. He is lost again in the eyes of Beatrice, and then much that our powers here cannot sustain is permitted there, asterisk, and in that instant we fly to the other side of space and of time. So how does the exterior of a white hole differ from the exterior of a black hole? If we are outside, floating in our spaceship at a safe distance, how can we tell the difference? How could we distinguish a black hole from a white one? The surprising and deeply counterintuitive answer is that we can't. Unless something is actively going into the horizon or coming out of it. From the outside, a white hole is utterly indistinguishable from a black hole. A black hole attracts things with its gravity, like every mass in the universe, and the same goes for a white one. Around a black hole, there may be planets or stars in stable orbits, and the same goes for a white hole. You can fall toward a black hole, and you can fall toward a white hole. From the outside, their gravitational fields are identical. This is deeply confusing. It feels wrong. A white hole is like a black hole that is rebounded, its film running in reverse. One might be tempted to expect that, by reversing time, gravitational attraction should become repulsion. But it is not so. Gravitational attraction does not become repulsion by reversing the direction of time. In a film of our solar system projected backward, the sun is still attracting the planets, which simply orbit in the opposite direction. In a film of a stone that is thrown upward and then falls back to Earth, even when projected in reverse, we still see the stone flying upward and then coming back downward, always attracted by the Earth. The gravitational field outside the hole does not change if the direction of time is reversed. Seen from the outside, a black hole and a white hole behave in the very same way. They are both simply masses that attract other masses through the force of gravity. How can this possibly be? They seem like such fundamentally different objects. You can only enter a black hole, and you can only exit a white hole. How is it possible that, despite this profound internal difference, they are indistinguishable from the outside? It seems like a glaring paradox. It is not. And it is here that the extraordinary subtle architectural magic of general relativity shines through in all its beauty. It is a delicate, beautiful, and intricate point. It is subtle and complex, and most people, even physicists, get lost here. It does not matter if you do. It is not essential for what follows. You can let this part of the explanation wash over you without compromising your understanding of the whole story. But if you do manage to follow the thread of the logic, you will be amazed by what the simple phrase, the relativity of time, truly encompasses. Here we go. A stone can exit from a white hole. Therefore, from the outside, I can see a stone freely moving away from a white hole's horizon. Now, can I see a stone moving freely away from a black hole's horizon? At first sight, this seems impossible. How can a stone move freely away from a black hole if nothing, absolutely nothing, can exit from it? And yet, it is possible. Here is how. If someone near the collapsing star throws a stone with great force directly away from the star, just a moment before the star's surface crosses the horizon, that stone will fly away and escape to safety. But seen from our vantage point, far away, the first part of that flight will take place in extreme slow motion, since everything near the horizon appears infinitely slowed down to a distant observer. The light from that escaping stone will take a very, very long time to climb out of the gravitational well and reach our eyes. The stone will end up moving away from the black hole for good only after a very long external time has passed. Hence, it is entirely possible for us to see a stone emerging, as if in slow motion, from the vicinity of a black hole at any later time. Thus, it is not impossible for us to see a stone freely moving away from a black hole, just as it is possible to see one moving away from a white hole. The argument also works perfectly the other way around. A stone falling toward a white hole cannot cross the horizon, because nothing can ever enter the horizon of a white hole. This would seem to indicate that from the outside, we could easily distinguish between a black hole and a white hole. It should suffice to simply observe a falling stone. If we see it entering the hole must be black. But remember, you can never see a stone enter the horizon of a black hole. Because the light from the stone takes longer and longer to travel away from the horizon as it gets closer, we can only see it approaching the horizon more and more slowly, getting redder and dimmer, without ever seeing it actually cross. And we see the very same thing for a stone that falls toward a white hole. We see it approaching the horizon gradually, getting slower and slower, without ever reaching it or entering it. So what actually happens to the stone that is falling toward a white hole? Before it can ever reach the horizon, it eventually collides with the matter and energy that is constantly rushing out of the white hole. This collision happens in a time that is very short for the stone itself, which encounters the outgoing matter before it gets to the horizon. But this time is extremely, unimaginably long when viewed from the outside. Once more, this is the key. Time slows to a crawl in the vicinity of the horizon. This is the magic of the elasticity of time. The black and the white horizons are themselves fundamentally different, but from the outside, they look precisely the same. The horizons and the interiors are what distinguish white from black, future from past. The exterior does not. Recall the title of that seminal 1958 work in which David Finkelstein first showed what happens at the horizon. Past-future asymmetry of the gravitational field of a point particle. The title itself underlines this central insight. The geometry of the outside of a black hole does not change with the reversal of time, but this symmetry between past and future is broken at the horizon. The horizon is not invariant with the reversal of time. The exterior is. It is for this precise reason that the same exterior gravitational field is compatible with both a black hole and a white hole, despite their horizons being so profoundly different. All of this seems almost incredible, like a magic trick played with time itself. But this is how Einstein's theory tells us nature works. Despite the complete and utter difference between what happens inside them, time's sleight of hand on their horizons allows a white hole and a black hole to be the same thing when viewed from the outside. And this was the crucial second observation that Hal made on that sunlit day in Marseille. Why was this so crucial? Because it makes it plausible that what happens inside the black hole is exactly what is illustrated in our diagram of the bouncing spacetime. The magic is that inside the horizon, the space evolves through the quantum bounce, transitioning from black to white, whereas outside the horizon, nothing at all happens. The external universe doesn't need to change. The quantum tunnel, the bounce, occurs only in the deep interior, in the regions of immense spatiotemporal distortion, in a way that is perfectly compatible with the fact that on the outside, where there is nothing extremely quantum happening, everything continues to respect the classical laws of general relativity as it should. The solution of Einstein's equations that black holes represent, and the one represented by white holes, can therefore be glued together seamlessly on the outside, without violating Einstein's equations in the region where we trust them. This is the pasting that Hal had suggested. The only violation of the classical equations occurs exactly where we expect it to, deep inside, where the distortions are so strong that they must produce quantum effects. Bingo! A light turns on. We have found a plausible, self-consistent scenario for what happens beyond the stopping of time. Beyond the classical singularity, there is the solution with time reversed, the interior of a white hole. Outside, for the rest of the universe, nothing dramatic happens. The black horizon, like Gandalf in the depths of Moria, has fought its battle in the abyss and has magically turned white. I remember the profound emotions of that day, the quiet joy and the buzzing excitement, as the scenario intuited by Hal began to come into sharp focus. The individual pieces of the puzzle were all known to us: the quantum tunnel effect, the mathematical solution of Einstein's equations that described white holes, the solution that described black holes, the theoretical existence of a lower limit to the divisibility of space from loop quantum gravity, the strange and paradoxical behaviors of white and black horizons, the scandalous temporal differences between what happens on the horizon and what is seen from afar, and the simple, powerful intuition that things that fall often rebound, and that Planck stars can do so too. All the pieces of the puzzle were on the table, and now they fit together. As in all such scientific puzzles, certain pieces that we thought were important fail to fit and must be discarded. What happens precisely to space and to time at the exact moment of the bounce? Quantum theory says that what happens during the leap does not have a description in our familiar language. It is a process that has neither a clear shape in space nor a duration in time. We can get a rough, intuitive idea of what happens if we imagine the crushing of the tube of space, gently slowing, coming to a halt, then rebounding from its direction of travel and beginning to expand again. But the deeper reality is that, in this transition, space and time dissolve into a cloud of pure probability, a foam of potentialities, after which they recoalesce and resume their familiar structure. The piece of the puzzle to jettison, the old idea we must be willing to let go of, is the notion that events in nature can always be imagined as if they were taking place in a pre-existing, smooth, continuous space and time. There were many questions that remained unanswered that evening. As the sun set over Marseille, we had to do the calculations. Good analogies are beautiful and essential, but to check that they are not illusory, you need the rigor of syllogisms, of mathematics. We needed to write down the equations to describe the geometry of our proposed spacetime, to demonstrate with mathematical proof that they are consistent with Einstein's equations everywhere except for the quantum transition. We needed to set up the calculation of the probability for this quantum leap to occur. We did this in the exciting days that followed. It was exhilarating and fun. A process of cutting and stitching different mathematical descriptions of spacetime, ensuring that the pieces fit together perfectly at the seams. The main problem was that each portion of spacetime was best described using a particular perspective, a particular set of mathematical coordinates that did not easily include the others. This was precisely the issue that had confused Einstein and everybody else from the very beginning, and that Finkelstein had so brilliantly clarified. The techniques for addressing this problem, for creating a patchwork quilt of different coordinate systems, are now familiar to relativists. We used them, and everything worked. The pieces clicked into place. We wrote an article with our results and published it. Slowly, cautiously, the idea began making its way into the scientific community. The hypothesis that a black hole can transform into a white hole was now in the hands of the world, available to whoever wanted to criticize it, improve it, test it, and help it grow. Yes, we were happy that night. There are few things in life as good as the rarefied, quiet lightness of this feeling. The feeling of having had a good idea, a beautiful idea, that might just turn out to be correct. The satisfaction of a long calculation that finally adds up. The quiet joy of an insight into how something might work, something that we did not understand before. It is a subtle happiness, subcutaneous but pervasive, as if one is suddenly feeling perfectly, harmoniously right with the world. Perhaps it is just the simple, honest feeling of having done a job well. The same deep satisfaction I get after having spent an afternoon carefully fixing the garden gate. Doing science is usually a long succession of frustrations and disappointments. It is a path of things that don't work, of wrong ideas, of experiments that fail, of calculations that do not add up, punctuated, only occasionally, by these brief, luminous moments of joy. Perhaps, though, there was something else that evening, the joy of taking a small step that satisfies, just for a moment, our deep, innate desire to understand, to go and see. Yes, we were very happy that evening, Hal and I, and yet, for all this, we were for sure very far from being convinced that we were in possession of a final truth. The history of science is replete with beautiful delusions, with elegant theories that turned out to be wrong. Might this be one too? Years have since passed. The idea of a transition from black to white has developed and been studied by many other physicists in various forms. We are now looking for possible observational evidence of this process in the sky. And yet, even today, I am far from convinced that we have the truth in our pocket. Scientists have a difficult, complicated relationship with their own ideas. Perhaps no one is ever completely honest, not even with oneself, about how much one truly believes. You need to be politically correct in the scientific community. You must be reasonable. You must always admit that you could be wrong. But deep in your heart, there is a mad, passionate desire to scream, "But I'm sure that this is how things are." One falls in love with one's own ideas, becomes convinced by them, and defends them tooth and nail. After all, our scientific reputation, which we cling to like children to candy, often depends on this. And yet, at the very bottom of our hearts, a quiet doubt is never fully quelled. The persistent, nagging fear that we are wrong, that we are deluded. Bittersweet is science. It will not have escaped the insightful listener that the key to Hal's idea, the hinge upon which this entire story turns, was time. A white hole is a black hole with time reversed. But is such a perfect reversal of time really possible? Most phenomena we observe in our daily lives occur in one direction only. Reversing them in time is not possible. A dropped egg shatters, but a shattered egg on the floor never spontaneously reassembles itself and leaps back into my hand. The past and the future seem profoundly, fundamentally different. The reconstruction of the life of a black hole I have given so far is too simple, because it neglects everything that distinguishes the past from the future. It ignores the countless phenomena that give time its arrow. To complete the picture, to make it more realistic, we now need to take into account the phenomena that cannot be reversed in time, the irreversible aspects in the life of black holes. And this leads us, once again, but now at a deeper level, toward fundamental questions about the very nature of time itself. What is it that makes the past and the future different? Why are they different at all? Why do we remember the past and not the future? Why is it possible for us to decide what we shall do tomorrow, but not what we did yesterday? I have been working closely with these questions, wrestling with them, over the last few years. This last part of our journey together is about these irreversible aspects in the life of a black hole. I will start with an amusing and ongoing controversy that currently has scientists squabbling. Then, I want to tell you about a number of things I think I have recently come to understand about the direction of time, ideas that seem quite beautiful and profound to me. In 1974, the brilliant physicist Stephen Hawking made a completely unexpected and revolutionary theoretical discovery. Black holes must emit heat. This, too, is a type of quantum tunnel effect, but a simpler one than the dramatic bounce of a Planck star. It involves pairs of virtual particles spontaneously appearing from the quantum vacuum near the horizon. Occasionally, one particle falls into the black hole while the other escapes, carrying energy away. In effect, photons and other particles that are trapped just inside the horizon can manage to escape, thanks to the pass that quantum physics provides to everything. They can tunnel their way out from beneath the horizon, so black holes are not completely black. They emit a faint thermal glow, like a warm stove, and Hawking was able to compute their precise temperature. This radiated heat, which we now call Hawking radiation, carries away energy. As it loses energy, the black hole must also lose mass, since mass is a form of energy, according to Einstein's famous E equals mc squared. As it loses mass, the black hole gradually becomes ever lighter and smaller. Its horizon shrinks. In the jargon of physics, we say that the black hole evaporates. The emission of heat is the most characteristic and fundamental of all irreversible processes. The processes that occur in one direction of time and cannot be reversed. A hot stove emits heat and warms a cold room. Have you ever seen the walls of a cold room spontaneously emit heat and use it to heat up a warm stove? Of course not. When heat is produced and dissipated, the process is irreversible. In fact, whenever any process is irreversible, some form of heat is produced, or something analogous to it, which we call an increase in entropy. Heat, or more precisely, entropy, is the definitive mark of irreversibility. Heat is what distinguishes the past from the future. It is the physical basis for the arrow of time. There is therefore at least one clearly irreversible aspect to the life of a black hole: the gradual shrinking of its horizon due to Hawking radiation. But be careful here, for another subtlety awaits us. The shrinking of the horizon does not mean that the interior volume of the black hole becomes smaller. The vast interior largely remains what it is, and in fact, the interior volume keeps growing as the tube of space continues to stretch. It is only the horizon, the gateway, that shrinks. This is a subtle geometrical point that confuses many people. Hawking radiation is a phenomenon that regards mainly the horizon, the boundary, not the deep interior of the hole. Therefore, a very old black hole turns out to have a very peculiar geometry, an enormous interior volume that continues to grow, and a minuscule horizon, because it has evaporated for billions of years, that encloses it. An old black hole is like a fantastical glass bottle in the hands of a skillful Murano glassblower who somehow succeeds in making the volume of the bottle increase, even as its neck becomes narrower and narrower. At the moment of the quantum leap from black to white, a black hole can therefore have an extremely small horizon and a truly vast interior. A tiny, microscopic shell containing vast, galaxy-sized spaces, like something from a fable or a dream. In fables, we often come across small huts or chests that, when entered, turn out to contain hundreds of vast rooms or even entire worlds. This seems impossible to us, the stuff of fairy tales. But it is not so. A vast space enclosed within a small sphere is a concrete physical possibility. If this seems bizarre to us, it is only because we have become so habituated to the idea that the geometry of space is simple. We assume it is the flat, predictable geometry we studied at school, the geometry of Euclid. But it is not so in the real world. The geometry of physical space is distorted by gravity, and this distortion permits a gigantic volume to be enclosed within a tiny sphere. The immense gravity of a Planck star, the bounced remnant of a black hole, generates just such a huge distortion. An ant that has always lived its life on a large, flat plaza will be utterly amazed when it discovers that through a small crack in the pavement, it has access to a vast, multi-level underground garage. It is the same for us with a black hole. What the amazement teaches us is that we should not have blind confidence in our habitual ideas about the world. The world is stranger, and more varied, and more beautiful than we typically imagine. The existence of these large volumes within small horizons has also generated a great deal of confusion and controversy in the world of science. The scientific community has split into factions and is currently quarreling about this very topic. In the rest of this section, I will tell you about this dispute. It is a bit more technical than the rest of the journey, so please feel free to skip it if you like, but it offers a living picture of a lively, ongoing scientific debate, a snapshot of science in the making. The disagreement concerns how much information you can cram into an entity that has a large internal volume but a very small surface area. One part of the scientific community is convinced that a black hole with a small horizon can contain only a small amount of information. Another part, to which I belong, disagrees. What does it mean to contain information? Imagine this. Are there more things in a box containing 5 large and heavy lead balls, or in a box that contains 20 small glass marbles? The answer, of course, depends on what you mean by more things. The 5 lead balls are bigger and weigh much more, so the first box certainly contains more matter, more substance, more energy, more stuff. In this sense, there are more things in the box of balls. But the number of marbles is greater than the number of balls. There are more distinct objects. In this sense, there are more things, more individual items, more details in the box of marbles. If we wanted to send signals by giving a unique color to each marble or each ball, we could send more distinct signals, more colors, more total information with the marbles, simply because there are more of them. More precisely, It takes more information to describe the state of all the marbles than it does to describe the state of all the balls, because there are more of them to describe. In technical terms, the box of balls contains more energy, whereas the box of marbles contains more information. An old black hole, one that has considerably evaporated for eons, has very little energy left because most of its initial energy has been carried away by the Hawking radiation. The question at the heart of the debate is this: can it still contain a large amount of information even after most of its energy is gone? Here is the source of the brawl. Some of my very brilliant colleagues have convinced themselves that it is simply not possible to cram a lot of information beneath a small surface area. That is, they have become convinced that when most of the black hole's energy has radiated away and its horizon has become minuscule, only a small amount of information can possibly remain inside. Another part of the scientific community, the part to which I belong, is convinced of the contrary. The information that has fallen into a black hole, even a greatly evaporated one with a tiny horizon, can still be large, stored safely in the vast interior volume. Each side is convinced that the other has gone astray and is making a fundamental error. Disagreements of this kind are common and indeed healthy in the history of science. One may say that they are the very salt of the discipline. They can last for a long time. Scientists split into camps. They quarrel, they scream, they wrangle, they scuffle, they jump at each other's throats at conferences. Then, gradually, over years or decades, clarity emerges. Someone's calculations are refined, a new experiment provides a crucial clue, or a new generation looks at the problem with fresh eyes. In the end, some end up being right and others end up being wrong. Adherents to the dogma that information is limited by surface area now find themselves stuck with a very difficult problem. They call it the black hole information paradox. They are convinced that inside an old evaporated black hole there is no longer any information. But we know that everything that falls into a black hole during its long life carries information with it. A book, a computer, an astronaut, they are all arrangements of matter that contain vast amounts of information. So a large amount of information can enter the hole. But quantum mechanics, one of the pillars of modern physics, has a fundamental law that states that information can never be truly destroyed. So if the information cannot be in the evaporated black hole, and it cannot be destroyed, where does it go? To solve this paradox of their own making, the devotees of the small horizon, small information dogma have been forced to imagine that the information escapes the hole in mysterious and baroque ways. Perhaps it is subtly encoded in the faint correlations of the outgoing Hawking radiation, like Ulysses and his companions escaping from the cave of the Cyclops by hiding beneath the woolly bellies of sheep. Or they speculate that the interior of a black hole is connected to the outside by hypothetical, invisible canals called wormholes, which act as information conduits. Basically, they are clutching at straws, looking, like all dogmatists in difficulty, for increasingly abstruse and complicated ways of saving their cherished dogma. But there is a simpler, more elegant solution. The information that enters the horizon does not need to escape by some arcane, magical means. It simply comes out, patiently and naturally, after the horizon has undergone its quantum transition and has been transformed from a black horizon into a white horizon. In his final years, Stephen Hawking himself used to remark, with a wisdom born of long contemplation, that there is no need to be afraid of the black holes of life. Sooner or later, he said, there will be a way out of them. There is, and it is via the child white hole. We are approaching the end of this story, the final leg of our journey. But the subtle and beautiful interconnections between the reversible and the irreversible aspects of time open up deep general questions about the nature of temporal flow, about the very meaning of time's passing. Before concluding my brief tale of black and white holes, I would like to address those larger questions a bit as well. The bounce from black to white is permitted by the underlying symmetry that comes from the reversal of time and the fundamental equations. But time in our universe clearly maintains its direction nevertheless. The precise moment of the quantum bounce might be symmetrical under time reversal, but the whole long process of a star's life, collapse, evaporation, and eventual dissipation is not. The tremendous temporal distortions created by black and white holes play havoc with our simple perception of time, but they do not seem to affect its fundamental orientation, the eternal current that carries everything forward. The past remains stubbornly different from the future. How so? Physics tells us something very strange indeed about the direction of time. And no doubt many questions would have occurred to the astute listener when I wrote above that the fundamental equations of physics do not distinguish between past and future. No direction of time, no arrow, comes from these deep equations. And yet I then went on to speak of irreversible phenomena, like the evaporation of a black hole, which are clearly oriented in time. Where, then, does the direction of time come from, if it is not inscribed in the fundamental grammar of the world? It comes from the fact that we and our universe are currently living in just one particular solution of the fundamental equations, and in this specific solution, the past appears special to us. The difference between past and future, that is a bit like the difference between two geographical directions for someone living on the side of a mountain. In one direction, say north, the ground goes up. In the other, say south, it goes down. But this is not because the concepts of north and south are intrinsically and fundamentally connected to up and down. It is only because things happen to be arranged in this way in that particular location. If you were on the opposite side of the same mountain, on the Italian side of Monte Bianco, for example, upward would be north, whereas on the French side, it would be south. The irresistible, one-way flow of time is similarly a local reflection of the way in which things happen to be arranged around us and in our cosmic past. The same goes for the life of our Planck star. The difference between the past and the future of the black hole does not come from a fundamental asymmetry that is intrinsic to time itself. It comes from the fact that the past state of the system happened to be a very particular, very special one, like the top of the mountain in our geography example. Think about it. In the future of the black hole, Hawking radiation fills the surrounding sky with dissipated energy, spreading it out everywhere. In the past, by contrast, all that energy was highly concentrated in the form of the collapsing star. The past was a particular, low-entropy, highly ordered state, because all the energy was concentrated in one place, instead of being dissipated and disordered as, in general, it is naturally found to be in the future. The direction of the past is special. Just as in any mountain village, the direction toward the single mountaintop is special. I have written at length about this basic underlying equivalence between the past and the future in my book, The Order of Time. But it is not an easy idea to digest. It goes against our most basic hardwired intuitions. Is it really possible that all the profound differences we experience between the past and the future come down to being just a contingent consequence of how things happen to be arranged in the distant past? Our intuition screams the opposite. It appears to tell us that the past is radically different from the future in its very nature. The very nature of reality, in our deepest intuition, is a flow, a happening in a directional time. The past is fixed, determined, and gone. The future is open, indeterminate, and yet to come. Is it possible that our fundamental sense of things can be so very wrong? And if it is wrong, why do we intuitively get things so deeply and consistently wrong? I asked myself these questions frequently over years of feverish work on white holes and their mind-bending temporal distortions, zigzagging between the reversible world of fundamental equations and the irreversible world of real phenomena. There are two phenomena that we know intimately from our own direct experience that radically distinguish the past from the future. They appear to be so basic and so banal as to make it seem impossible to entertain the idea that time by itself has no intrinsic direction. They are two very vivid asymmetries between past and future, which seem absolutely irreducible. The first is that we know things about the past, but we do not know the future. So the past appears fixed, determined, knowable. The second is that we feel we can choose the future, but we cannot choose the past. The future appears to be open, indeterminate, subject to our will. Is it possible that such apparently fundamental, essential differences between the past and the future are just accidents of the particular configuration of things in our universe? This is an astounding thought, but it is something that, I believe, we can now untangle. And now we can finally get to the key point, the heart of the matter. Look again at the last figure, at the water pouring through the interconnection between the two tanks. If you were to see only a snapshot of that wave in motion, without any other information, you could still tell that the bulkhead was recently opened. The wave itself is a testament, a physical record of the fact that something happened just before the opening of the bulkhead. Something in the state of the present tells us of an event in the past. Traces, records, fossils, photographs, memories. They are all irreversible phenomena like this wave. For them to occur, for a trace of the past to be imprinted on the present, it is enough that the three simple conditions I have listed are present. 1. There are systems that start out in a state of disequilibrium, which, 2, are allowed to occasionally interact. And 3, the system that preserves the trace, the memory, the record, like the surface of the water, or a photographic film, or our brain, must in turn remain away from equilibrium for a while. The initial disequilibrium of the early universe, the fact that it started in a very ordered low-entropy state, is the ultimate reason why the present has traces of the past. The formation of every single trace, every memory, is nothing other than an intermediate step in the universe's long, slow journey toward equilibrium. If the present has traces of the past, it is due solely and entirely to the disequilibrium of that past. It is for this reason, and this reason alone, that we remember the past and not the future, because of the vast reservoir of order or disequilibrium in the past. We know the past because there are physical traces of it all around us in the present, in our memories stored in our neurons, for example. To say that the past is determined is to say no more than that we are surrounded by a multitude of consistent traces of it. It is not some intrinsic directionality built into time itself that makes the past knowable and determined. What we call the past is simply how things happen to be arranged at one particular point in time. It is the initial disequilibrium of the past, and only that gives rise to the existence of traces, and thus to our perception of a fixed past and an open future. The second profound phenomenon that seems to contradict the fundamental similarity of past and future, a phenomenon that concerns us even more intimately than memory, is the fact that we feel we can choose the future, but we cannot choose the past. We decide. When we make a decision, we consider the pros and the cons. We assess the available information. We consult our memories of past experiences. We assess our long-term objectives. We take our moral values into account. We weigh our conflicting motivations, our desires, our deepest ethical convictions, and so on. And at the end of this complex internal process, we decide, yes, all things considered, I am going to get the bar of chocolate from the cupboard. Making a decision can be an incredibly complex process. A sophisticated computer that plays chess and thinks long about it before making a move is doing something similar to what we do, albeit in a less rich and complex way. Making a decision is simply the name that we give to this complicated physical process that takes place between our neurons before an action is initiated. There is nothing strange about this. The world is full of complicated physical processes, but there is a radical aspect to our experience of decisions. We feel that we can decide freely. Whether at the end of a long and troubled process of rational evaluation, or intuitively and without thinking, we feel that it is we who decide, spontaneously, in a way that cannot be perfectly anticipated, even by ourselves. The world can evolve, following this free decision of ours, toward different possible futures. After all, we feel we might not have eaten the bar of chocolate, or so we tell ourselves after having eaten it. We feel we can freely decide, but only about the future, never about the past. Where does this profound temporal asymmetry of choice come from? The answer, once again, is the same. It is the result of the state of disequilibrium of the world we happen to live in. A decision, just like the formation of a memory, is an irreversible physical process, a step toward equilibrium. The freedom of our choice is real, but it is a feature that regards the macroscopic description of what happens in our brains, not the microscopic one. It is the macro story that appears to branch into multiple possibilities. This is possible because many different macroscopic futures are compatible with the same macroscopic past. And this, in turn, is possible precisely because a vast number of different microscopic pasts all look identical from a macroscopic point of view. This freedom that we search for, and which is so dear to us, is real. But as the great philosopher Baruch Spinoza clarified with startling lucidity in the 17th century, our feeling of freedom is our way of designating the fact that we are not able to fully reconstruct what happens in our own decision-making process, and thus we are unable to perfectly predict what we will decide. Spinoza writes, "Men feel free because they are aware of their choices and their wishes, but they ignore the causes that lead them to will and to choose, and do not give the slightest attention to these causes." And again, men think that of their own free will they can do something or refrain from doing it, opinions that consist only of this, that they ignore the causes that make them act as they do. There are those, strangely, who are disturbed by this scientific and philosophical understanding of what our freedom actually means. I think they are making a mistake. It is the old fisherman's mistake. Once upon a time, there was an old fisherman who loved the sunset more than anything else in the world. Every evening he would sit on the shore and watch as the horizon exploded with fiery colors, as the sun descended majestically and slowly plunged into the ocean, as the sky was colored with the sweet color of oriental sapphire, and as, one by one, the first stars appeared. Then one day, a visitor from the city, a clever man, came and said to the old fisherman, "You know, my friend, the sun does not actually sink into the sea. The sun is still out there, always shining. The beautiful show you see every evening is just a trick of perspective, an illusion caused by the rotation of the planet that we're standing on." The old fisherman was astonished. He trusted the man from the city, who seemed to know many things. He began to be troubled. "The sunset is an illusion," the man had said, "and therefore it is not real." For all these years the fisherman had been absorbed and fascinated by an unreal event. He had been tricked by his senses his entire life. If the sunset is an illusion, he now thinks, then it cannot be relied upon. He must learn to do without sunsets. He attempts to do so, and it is a disaster. He no longer knows when to go to sleep. In the evening he does not expect the night to come, and when the beautiful sunset arrives, he stubbornly repeats to himself, "It's an illusion. It's not true. There's no such thing as a sunset. The sun does not sink into the sea. The sun always shines. I have to take reality seriously. I do not have to go to sleep." He never sleeps again. He ends up going insane. The old man was obviously committing an error, but it was a subtle one. The question that disturbed him so deeply was whether the sunset was real or illusory. He learns that the sun does not literally sink into the sea. From this, he concludes that there is no such thing as a sunset. But we, who have known since Copernicus that the earth moves, still speak calmly and happily about sunsets. We enjoy them, we paint them, we write poems about them, we rely on them to mark the end of our day, and it does not cross our minds for a moment to say that there is no such thing as a sunset. We have simply readjusted our notion of what a sunset is. For us, a sunset is real. It is the beautiful, reliable phenomenon that we have always seen. But it is no longer defined as the sun sinking into the sea. It is, if we really want to think about it with our scientific minds, the name we give to the phenomenon that occurs when the rotation of the Earth carries us away from the part of the planet that is illuminated by the sun. It is still the same sunset. Its beauty is undiminished. Its reality is intact. So why should we be disturbed to discover that the flow of time, the distinction between past and future, is a perspective phenomenon? Why should we be troubled to learn that our precious freedom is a macroscopic phenomenon that is not borne out at the microscopic level of individual particles? This is the same kind of discovery as learning that the sunset is not the sun sinking into the sea. It changes nothing fundamental in our lives, in our experience, in our responsibility for our actions. But it redefines, in a profound and beautiful way, what we mean by the flow of time. It is nothing other than the name we give to a particular perspective on a peculiar, unbalanced arrangement of things in the universe. In a universe that was in complete thermal equilibrium, as in our tank of water after the wave has completely subsided, there would be no irreversible phenomena at all, and thus nothing to allow us to distinguish the past from the future. We could not say in which direction time flows. But there would be a far more radical and personal consequence for us in such a universe. Our very thoughts could not exist. We would not be able to make observations or to reason or to remember, because to think is to process information, and processing information is a physical process that dissipates energy and increases entropy. We would not have senses, because our senses work by recording things. In other words, they produce memories, which are irreversible imprints. Our senses simply would not work in a situation of perfect equilibrium. We would not be able to hear music, since music exists in our heads only because our memory can hold on to the preceding notes while we hear the current one. In a universe in perfect equilibrium, we would simply not exist as thinking and feeling beings. It is because this state of disequilibrium is so fundamentally necessary for thinking that it is so natural for us to think of time as being intrinsically directional, and so difficult for us to accept the idea that the orientation of time is not a fundamental property of the universe. The time of our thinking is directional, because our thinking is itself an irreversible phenomenon. We are irreversible phenomena. We are, in the deepest sense, children of time's arrow. We have the complete picture now. Our journey is coming to its end. A large, cold cloud of hydrogen gas, sailing silently through the vast empty spaces between the stars, begins to slowly get denser under the gentle pull of its own gravity. As it contracts, it fragments and heats up until its core becomes so hot and dense that it ignites with nuclear fire and becomes a star. The hydrogen in its core burns for billions of years, creating light and life until it is wholly transformed into helium and other, heavier ashes. With its fuel spent, gravity becomes irresistible, and the star collapses catastrophically into a black hole. Other, smaller black holes can perhaps form in the unimaginable inferno of the primordial universe, when the fluctuations in temperature of everything were violently extreme. However it is formed, the matter of the collapsed star sinks and rapidly reaches the center. Here, the fundamental quantum structure of space and of time itself prevents it from being crushed any further. It cannot be squeezed into a point of infinite density, because space itself is made of finite grains. It has become a Planck star. It then bounces and begins to violently explode outward. Around it, inside the old horizon, space itself completes a quantum leap, and its geometry rearranges itself, transforming like Gandalf from gray to white. This incredible process of transition is of the same fundamental kind that may have produced our own Big Bang, possibly from the collapse of a previous universe. Space and time dissolve into a probabilistic foam and then reform. It's a process that is outside of time and outside of space as we know them, and yet